clarify that each packet is 5 through 10. So find one pile, and then there should be one up there that says Unit 9. If you don't have it at home, then it's on Canvas. All right, so we're looking at this, where it says parametric equations. Quick little review at the top there. Just remember how we define, in this case, parabolic equations, so parabolas, circles, and ellipses. Those equations are going to pop up today. So just recall what those look like. In particular, the circles, ellipses, we haven't dealt with those much at all this year. You're certainly going to deal with them now in this chapter. All right, so those are equations, old ideas, just recall what those all mean and look like. A little definition, a relation is a set of ordered pairs. A graph of a relation then is in taking that set of ordered pairs, putting them in the XY plane. And then a parametric equation. So now when we start talking about parametric equations, what this idea deals with is the fact that X and Y are defined with a different variable, usually a t, because eventually that's going to reflect time. What a parametric equation start to allow us to do, most of what we've been doing is single variable, where you're just going left, right, up, or down. Now that we're going to define these things parametrically, we can actually have and measure horizontal change and vertical change at the same time. Like how far horizontally did we go, while at the same time increasing vertically or decreasing vertically. And we can do that through what's called the parametric equation. It will look many times like this, that my function x is some function of t, and my y position at any point is some function of t as well. That would then mean that my coordinates, my location, my position, x comma y, would be whatever my functional value for f is, and then whatever my functional value for g is. We can write that as an ordered pair. That's going to tell us our location. So the first thing we want to kind of do, so if you have your calculators, pull that out. So it says using your calculators, you're going to graph the following relations. Let me get my calculator ready. And right now, if you try to graph this, that's a problem, right? Like we have x equals and then a root t. So how could we possibly make that happen? So if you go to your calculator, it's kind of blurry in here. Let's see if I make this. Whoa, that's weird. I do not know what this just did. What the heck? I've never seen the screen before. What? I think it's frozen more than anything. Oh. That's not good. Do me a favor. I'm going to close this down and restart it. Go to where it says, I got it, mode. So up here at mode, click on that. I got to close this down. And then when you go to mode, you should see a whole bunch of options. Scroll on down to where it says function, and then next to function, you're going to see a PARA, you're going to see a POL, and you're going to see an SEQ. Go down to that option. We're dealing with parametric, so when you see the PARA, move your little arrow over so that that PARA, the para word, is highlighted. Hit enter. Now go act like you're going to graph something. And it should look drastically different than what you're used to seeing, correct? Look at your paper. Hopefully at some point in time it'll pop back up here, and hopefully this works now. What the heck? Good call. Good call. That's what that was. Who was that, Safian? You're a good man, Safian. I don't care what Brian says about you. That was very helpful. Yeah. All right. So now I should be able to go to the. Oh, I haven't changed mine yet. So mode. Scroll on down to where it says. You fancy ones now actually say the word parametric, so that's nice. And then this should not look like what we just talked about. We're going to define x in terms of a third variable. We're going to define y in terms of a third variable. Our notes, we're going to do root t as x and then t as y. So do square root t, and then fancy, right? Like for the first time, you don't always get the x pop up. Now it's actually going to be the variable t, so that's clever. And then the y is just going to be a regular t. If you look at your window, however, that I gave you on the paper, I tell you I only want t values greater than or equal to 0. So now go to your window that we normally would go to. Notice how I have my t as a 0. You can't really put infinity in here. I'll put a 10. That'll be plenty big enough. And when we now graph this, notice what this would now look like. See how it's kind of a half a parabola? That should be what we're all looking at if your window is standard. That's what this graph is going to look like. So for right now, that's what I want you to do, is just kind of sketch that in. So take this, we started at the origin, and then we had a parabola that looked like this. Not coincidentally, we had a restricted time range. Only 0 is greater than infinity. Decent chance, and that's why we don't get the entire parabola, because these should all be parabolas. If we now go to this one, where I give you negative infinity to infinity, same thing. Go ahead and graph t and then t squared. So t, oh, here's one of those. Window-wise, you can't put negative infinity to infinity, so I'll go negative time from a negative 10 to positive 10. T doesn't necessarily mean time, but when we start using this a lot, that's what it's going to reference, so I'll say time. Notice how now that gives me the entire parabola. So we get an entire parabola centered at the origin, or vertex is at the origin, and it opens upwards. So then sketch that in, and then that's our graph as a rough sketch. So then what I want to do is let's show why we actually now get these. And it's really just some simple little algebra right here. If I did this with number 1, if you think about what this is saying, notice how y is equivalent to t right here. So if I took the first equation, x equals root t, well, isn't y equivalent to t? So can't I erase this t, replace it with what it's equivalent to in the second equation, which is a y? If I now square both sides, don't I just get the equation of a basic parabola with no shifts in it? Right, what you would call the parent graph back in the day when you did all those shifts and everything, we just get y equals x squared. Largely the same with this one. What I'm going to do in this case, let's take y equals t squared. So y equals t squared. And don't I tell you right here that t is equivalent to x? So can't we really just get rid of this x, or t, and replace it with x? And aren't we looking at that same exact parent graph of y equals x squared? Okay, so that's why parametrically these are giving us parabolas. All right. All right, next one's circles. This we have not talked about in a while. So here's the equation I want you to plug in. So do a cosine of t, a sine of t. You're not plugging in the variable a. I'm telling you what a is going to equal here. So let the x be your cosine, let y be sine. All a is the coefficients. So we go to our graph and we're going to do cosine. I'll actually plug in the 1 just so we know what the a stands for. So a was a 1, and then I want the cosine of t. And then the other one, a is a 1. I want the sine of t. Hit graph, it should give us a circle, right? And when we get that circle, understand it's a rectangular window. It looks more like an ellipse, kind of like an oval, but the radius is definitely 1 all the way around. So it's definitely a circle. Notice how our radius is a 1. So on our notes, sketch that in real quick. We have a circle that's centered at the origin with a radius of 1. And then give me 1 second here. Yeah. Number 4, go ahead and do this so that our a is now a 2. So don't rewrite it. Just get over the 1, put a 2 in for the 1, put a 2 in for this one, hit graph. Notice how we get a circle once again. Now it is simply a radius of 2. So this is our graph here. I should be mentioning this also because eventually this is going to change. Notice this is 0 to 2 pi. This was 0 to 2 pi. We should probably be changing our window to be that. So let's do that in number 5 to see if that changes. So for number 5, go ahead and let the a's be a 3. So 3. If I think we're all catching on here, we would anticipate this probably being a circle with a radius of 3 now. But go to your window. Let's actually change it to what I'm telling you to change it to. Go 0 to pi. Or I'm sorry, 0 to 2 pi. Hit graph. And we still get a circle with a radius of 2 centered at the origin. So now, without our calculator, just kind of anticipate what do you think is going to happen with this fourth one. So let me draw on the third one here. So now we just have a radius of 3. So before you use your calculator, sketch what you think this would look like. And then use your calculator, confirm whether or not your initial thought was correct. Because probably it is. I'm going to guess that most of us are understanding what this should look like, and then just confirm it with our calculator. I do not. I still have the ghetto old-fashioned battery calculator. Sorry. You find random stuff in my room sometimes. What's the charger look like? I'll look in a minute. Keep looking. I got a lot of stuff left in my room, so I might have an extra. All right. Hopefully, when we now graph this, do we get a circle with a radius of 1 that we hopefully would anticipate? And then now that we limit this, think about unit circle values right now. Wouldn't that give us a quadrant 1 and a quadrant 2? That's probably what we would have anticipated. Is that what we then actually get? Yeah. So we should have a semicircle now in this case with a radius of 1 centered at the origin in the first and the second quadrant. All right. One more, I think. Yeah. And then we'll talk about how we're going to get a circle out of these. So how could we do this algebraically if we didn't have a calculator in our hand or something? Looking at this, hopefully we know now that coefficient is giving us the radius of our circle. So it should be 2. And then if we look at this, we would anticipate if we're doing unit circle stuff, wouldn't that give us our circle down here in quadrant 3? All right, is that in fact what the calculator tells us that we get? Yeah, so it should be a quarter circle now with a radius of 2 centered at the origin. The quarter ends up in that third quadrant. All right, so now the question is, how do we get a circle? So recopy, since I don't on this page, they're on the previous page. Here's what the 2 equations are that you're entering. So rewrite that here. Oh yeah, that's good. Yeah. Well, off my game today. Let's see here. Yeah, that's definitely second quadrant. Thank you. Sorry about that. It's nice having people in here. Tell me. All right, so now let's go the second part here. And let's show how we're getting circles. Like, why are we getting circles with these? What's the relationship that's allowing this to happen? And I kind of give you a little hint here. Solve for cosine. So let's just divide that a over on both of these. And then over here, you're solving for the sine. The identity that everybody remembers is cosine squared, I'll use t's in this case, plus sine squared of t equals a 1. That's one that everybody remembers. Well, let's do some substitutions. Doesn't cosine in this case equal x over a squared? And then our sine over here, sine is equal to the y over a. So we would do y over a squared equals a 1. So if we now simplify this, what we would get is x squared over a squared plus y squared over a squared would equal 1. Create a little space here. Multiply everything by a squared, and don't we now get this part of it? So we're centered at the origin because we just have x squared plus y squared, and what that would equal is a squared. And in a circle, this is always your radius squared. So this is just showing us that a corresponds to the radius of each one of these circles or semicircles, quarter circles, whatever amount of it that we have. Okay, 8. Ellipses, also something we haven't talked about in a while. Actually, sketch this in. Take a guess at what you think this would look like. So we've done enough with the circles. You could probably make a pretty good educated guess about what this would look like. So x is still the cosine, b is sine, a is going to be 2, b is going to be 3. And if you get an ellipse, then there's at least a reasonable chance that you're right, because I'm telling you these should all be ellipses. So that's a good start. And then see if it's confirmed or not. If this was a 2, so I'm going to put the 2 in for cosine, and then my b is going to become a 3, so 3 sine of t. Notice how x is equal to the 2 cosine. My guess, hopefully, that we would kind of assume that the x's would have a, I'll use the word radius, it's obviously not a radius, but left and right, that length would be 2 and negative 2. And then with our b being a 3 for the y coordinate, that radius slash length along the y-axis should be down here at 3 and negative 3. And when we connect those, we would get an ellipse. Don't judge me too badly on my drawing there. What I do want you to now do, throw this into the calculator. So let me throw it into mine too, so I can point out what we would now want to look for, because I'm going to ask this question here in a minute. So I had 2 cosine, 3 sine. Yeah. All right, so when I hit graph, so here's our equation. One of the things you're going to get asked about a lot, because this very much transitions into vectors here in a few days. And vectors are directed line segments, and the direction in which you're traveling, those sorts of things are going to become pretty prominent. So when I now ask you the direction in which we are traveling, because this is just a different way of measuring direction and motion and velocity and all that stuff. When I hit graph, notice where this graph is going to start. Notice the direction that it's going to be going in. So when I hit graph, it's going to be quick. All right, see how that's going in a counterclockwise direction. One of the things I'm going to ask you to do, so we'll do it here for the first time, is show the direction in which this is moving. So with little arrows, we're going to show that this is the type of motion that we had. We're going in that counterclockwise direction. It is an ellipse. We go 3 up and down, 2 left and right. Okay. So same with this one. Probably don't need our calculator at this point. Now that this is the coefficient of our x, our cosine, that means we're going to go to a positive 3 along the x-axis and a negative 3 along the x-axis. The b is the coefficient for your y sine of t. So that means we're only going to go up to 1 and negative 1. So now we're going to get kind of like a football ellipse. But when we graph this, this should have also have been going, you can use your calculator if you want to confirm that. That also goes in a counterclockwise direction. Last one of these, go ahead and do that. And again, hopefully we can do this without necessarily having to graph it. I am going to graph this one because we have a follow-up question that I want to kind of show and talk about. So that's an ellipse. We go left and right 2. We go up and down 4. So let me change that on my calculator real quick. So 2 and 4. All right, so same process. Look where this starts and look in the direction that it's traveling in. So it's going to start right here, and it went in that counterclockwise direction. The next question that's part of this one is, what if we make our t a negative t? So let me insert a negative in front of the t for both of these. So now watch when we graph this. Look at where it starts. Look at our direction. So notice how it should start at the same spot, but see how that goes in an opposite direction? So when we answer that particular question, what happens if your t is negative? You're just going to put that this changes directions. The direction of motion is now reversed. Here's what we want to understand out of this. And again, even though it's hard to monitor calculator use, most of the stuff eventually becomes non-calculator. On the unit circle, doesn't the x always correspond to the cosine? And then doesn't y always correspond to y? So as long as the x is paired with cosine and the y is paired with sine, it's behaving like the unit circle. That's why we can look at 0 to 2 pi, know it's going to be a full circle. That's why if we go up to number 7 and we look at pi over 2 to pi, we would know, unless you're me, who thought it was in the third quadrant, you would know that this has to be our second quadrant because it's pi over 2 to pi. However, let's switch those around. So you don't necessarily have this problem on there, but look at this here. Let me delete the negative so that doesn't play a role in anything. Let's let x get paired with sine and let your y get paired with cosine. When I hit start, you can do it on your own too. You'll be able to watch on the screen when I hit it. Look at where this starts and then look at the direction of motion. So when I now hit graph, see if it still starts at the normal spot. It doesn't. Notice how it started up here, and notice how that also took us in a clockwise direction, the opposite direction. So be really, really aware of that. Don't always think we're going counterclockwise. Don't always think you're going to start on the x-axis, the positive x-axis. It really depends on what's paired with each other. If x is with a cosine, y is with a sine, then yeah, it's going to behave just like our unit circle would lead us to believe. All right, so then next question, how do we get an ellipse out of these? So why are these producing ellipses all the time? So take the original problem. I have a cosine of t, and then y is equal to the b sine of t. Same exact identity. So let's say cosine squared of t plus the sine squared of t is going to equal a 1. Cosine in this case is x over a, if we solve that. And then sine for these is the y over the b. So do those substitutions. So instead of cosine squared, I'm going to do x over a. Instead of the sine squared, we're going to do the y over the b. Isn't that basically right off the bat, isn't that what the equation of an ellipse would look like? You will a lot of times see them both squared, so x squared. And you would have talked like major axis, minor axis, all that fun stuff. So the a and b are those axes links. Come on, work. And then for the ellipse equation, it should have always been equal to a 1. So that's why we're getting ellipses out of those. All right. Last but not least, do this on your calculator. See what this looks like. This, now we probably don't know what it's going to, we know it's going to be a line because I tell you it's a line. But go ahead and do it on the calculator to see what it looks like. And even the word line is maybe not accurate here because we want to go 0 to 1 only. So don't tell Mr. Farina I have this written in as a line because he's our resident geometry freak here. Because this would more appropriately be called a line segment, correct? It's not all of it because we just have this limited interval. So what should that be? So you should have saw a graph that does what? Starts up here and then goes to here. All right, we agree with that. Notice how this would have been your first point, because this is what we're going to do next. This is where the graph is. So when you hit enter on the calculator, didn't it start at the top point and then it went in this direction? So start putting those arrows in, because that's what I'm going to have you do now in these next set of problems, is understanding that direction. And now it's starting to kind of look like a vector, right? Like a directed line segment. All right, so now long term, here's what we want to be able to do. So let's pretend you weren't able to have your calculator out all the time. So without using a calculator, find a Cartesian equation. That just means an XY equation. So don't freak out about that. So just an equation in terms of X's and Y's, normal looking equations for the path of motion. Then you're going to graph the equation, and then you're going to show the direction in which the particle travels. So for this one here, when we go to graph this, here's what we really want to do without our calculator in the hand. So what we want to set up here, instead of a XY chart, we really now have 3 variables in play. So we're going to set up what's called a TXY chart. We know what this should look like, right? Like we should be able to do this. So we're going to confirm this one. This, hopefully we all look and know X is paired with cosine, Y is paired with sine. That's what the normal unit circle looks like. The coefficients are both 1, so this should be a circle with a radius of 1. However, over these intervals, 0 to pi, it would end up being a semicircle. So what this should look like, so we can go ahead and sketch this in, and then we'll show how the TXY chart would work as these become a little trickier. This should start here like the normal unit circle does. It should then go counterclockwise, so we can give it this direction, and then it should finish over here at pi. Here's how we can now do that with our little chart. So since we're starting here at 0, that's the interval for our time. Just plug that in and get your X position and your Y position at that particular time. So the X is cosine of t. So you're going to plug in your 0. The cosine of 0 is a 1. Plug in your time of 0 at the sine. That's going to be a 0. So not coincidentally, this is at the time of 0. So at the beginning of time, that's our initial position. That's our X position, that's our Y position. Don't be too specific and, you know, have overkill. Let's just jump right to pi over 2. We know this is going to be some sort of a circle. Now the cosine of pi over 2 is our 0. And then our Y coordinate is the sine of pi over 2, which is going to be a 1. So notice how this was our second equation, our second point. That's why we knew if this was our first time, and this is the next time that we plugged in, that's how we would know we went in this direction, because we started here and this was the next point we found. We know we're going now in that direction. And then if I go to pi, we should get values of -1 and 0. That would tell us this is our terminal point. This is where we end up. Okay. The equation, hopefully I left enough room in here, is the whole cosine squared t plus a sine squared of t equals a 1. Well, that's, in this case, cosine is just x, sine is just a y. So this would be the equation of a circle that's centered at the origin with a radius of 1. And then our domain is just limited by the interval that I gave you. All right. All right, so 13. Once again, the x is paired with cosine, the y is paired with our sine. So we could probably sketch this without our chart. We would know that we go right 4, left 4. Our y's are going to be 5, -5, go a little further for the -5. We only want to go 0 to pi, but this should behave very much like the unit circle. So this should take us first and second quadrant only. So this graph should look like half of a ellipse. Because it's the same as the unit circle, it should go counterclockwise, just like the unit circle does. So we can indicate that. That's what should play out with our little chart. So let's set that up. So start at 0, and then we'll use pi over 2 and pi. And then watch how this would give us this information too, if it wasn't an easy one that we already knew. Cosine of 0 would have been a 1, and then you're going to multiply by 4. So your x position at that time would have been 4. Your vertical position would be 0, because the sine of 0 is 0. So that tells us this is our initial position. Pi over 2, now the cosine of pi over 2 is our 0. The sine of pi over 2 is a 1. Multiply that by 5. So this would have been our second point up here. So that means we started here, we went next to this point. That then is largely enough. You may want to do your last one. That should give you a negative 4, 0 to see where we stop. And then that's our graph. Then the equation for this, x over 4 is the cosine of t for this one. Y over 5 is equal to sine of t. And then we know cosine squared plus sine squared equals 1. So our equation in this case would be x over 4 squared plus y over 5 squared is equal to 1. Those are pretty easy to predict, the circles and the ellipses, if we just understand, is it unit circle stuff or is it not? Jump to number 14. And let's try this guy, because this one's a little trickier. If you try to do this graph without your calculator, I would think you'd find it a little bit harder. So now this little TXY chart, you may be thinking in 12 and 13, I didn't really need that. You were probably right. 14 and 15, though, you're going to want it. So for us to graph this, now we really want to kind of figure out what are these points. So T and then X and then 1. Clearly our initial T has to be a 0. So just start with a 0. Pretty straightforward. You're going to get 0, 0. So go to our graph. We definitely start at 0, 0. I'll just pick 1. It works out nicely. This would be a negative root 1. So that's a negative 1. And then your y coordinate is a 1. So I'm going to come over here. My x position is a negative 1. My y position is a positive 1. So I'm there. Pick a good number. Don't pick 2. Don't pick 3. Pick 4 so that we can take the square root of it nicely. This should give us a negative 2, 4. So then I come over here to negative 2, 4. If we didn't know this is supposed to be a parabola, now we should, right? Like we can see this is a parabola going in this direction. So if I now ask you which direction this is traveling in, since this was our first point, this was our second point, this was our third point, we knew this was the direction in which we were traveling. Okay. The equation, I'm just going to do a straight substitution. Here's t. Doesn't t equal y? So I could just say x equals a negative root y. That's actually okay. There's nothing wrong with that. That actually gives us this graph. If you square both sides, then you're going to see definitely a parabola, but just on a limited interval, we get y equals x squared. All right. Oh boy, I gotta hustle. I'm going to get this done. All right, 15. Definitely want a little TXY chart for this. We should know, notice how both of these degrees are 1. 1 minus t to the first, 1 plus t to the first. This is a line. If our degrees are 1, still linear, both of them are going to be a 1. So set up your little chart. We need to know what are some points on this line. Obviously, you can't plug in a negative infinity. You can really pick whatever you want. I'm going to pick 0, and my initial point is 1, 1. As long as we know it's a line, we only need 2 points to make a line, correct? So we really just pick one more value. I'll pick a 1. That make this hard. Then I get x to be 0, and I would get y to be a 2. So then I'm here. So since this was my first point, and this was my second point, that tells us that we are moving along this line in this direction. So now be very, 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 very careful. Because what we no longer want to do, hopefully the bell doesn't interrupt this, we don't want to put an arrow right here, because now the arrows mean something. they give us our direction. So the way to show that this continues from this direction forever, put like, it makes it actually kind of look like an arrow. At the end of this thing, put your arrow saying that we are coming from this direction forever, but we are moving in this direction. Okay. And then you can do some substitutions real quick. Do your line. We can all do that. It's just a little substitution. Solve for X or solve for Y. Plug it in, and you'll be able to get that in terms of X and Y equation. All right. Right on time. Perfect. All right. We'll see you guys. Have a good night. All right. Bye, Aaron.
Hoping to get some sort of like conference schedule soon.
I know, right? So you can actually put